All right, welcome to another unit here, Unit 9 now, Soil and Glass Analysis. So those may seem like very different types of physical evidence, soil and glass, but they actually have very similar methods of comparison, and we'll talk about why they belong together here in Unit 9, Soil and Glass Analysis. Okay, so if we want to think about soil, let's think about the earth first. And so we'll go back to, I don't know, elementary school, middle school, and talk about the different layers of the earth. So at the very center, we have our inner core, which is mostly iron solid inner core. And again, that's due to the tremendous pressure it's under that it's able to be a solid. And we have magnetic data that suggests it's a mostly iron core. So that's why without ever having sampled the center of the earth, we have a pretty good idea of its chemical makeup. Beyond that is the outer core. Now this is a liquid. It's not under quite as much pressure as the inner core, but it's still mostly iron, and again we have the magnetic data to back that up. The mantle is the next layer. This is actually the largest layer by volume, and it's mostly solid rock there. And finally, the crust is what we walk on. It's a very thin, almost like the shell of an egg compared to those other layers. It's quite thin, but it's, again, thick enough that that's the layer we interface with. So in forensic science, it's the physical evidence from the crust that's going to be important in essentially all of the criminal cases that will look at soil samples and geologic evidence. So if the crust is the most important from a forensic standpoint, then let's talk a little bit more about Earth's crust. So the crust is created by the weathering of that underlying rock. That's how we get that exposed soil that is most often what we would discuss in forensic analysis. So really the crust is mainly composed of just 8 elements, and the overwhelming majority of those elements are just the two, oxygen and silicon. Now this is not the oxygen in the air. This is oxygen chemically bound to different species. So since we've got well over 70% due to oxygen and silicon, it makes sense that the most common mineral in the Earth's crust is quartz, which is a chemical made up of silicon and oxygen, silicon dioxide, 2 oxygens chemically bound to each silicon there. Other substances that are of note, aluminum's number 3 there with 8.1%. And again, you'd think in the modern world, with all of our use of aluminum foil just to cook on and toss out, you'd think that aluminum's very plentiful, and you'd be right, but it was actually quite a while before we figured out how to make the metal. The metal doesn't occur in nature, just like silicon doesn't occur freely in nature. Aluminum and silicon occur in the natural world as compounds. So it took quite a while to figure out how to cheaply and easily convert aluminum in its oxides, or bauxite's actually the most common ore, but to take it from its compounds and make it into the metal. Speaking of another metal, iron. Iron we figured out a lot longer ago, so you can think about the Iron Age and things like that in terms of anthropological dating of civilizations by the materials that they were able to use. So iron is number 4 in terms of its abundance, but again, we've had a lot of experience with iron much earlier than aluminum in terms of the metal. Calcium, it's another one that doesn't occur as a free metal, but we can make metallic calcium nowadays. It's not terribly useful for a lot of things because it's so reactive, but in chemistry, calcium, potassium, sodium, those next few, we can make the metals, but again, it's mainly compounds that we observe those in nature. Magnesium, we do use the metal sometimes there for lightweight applications along with aluminum. So things like aircraft, you might have magnesium or aluminum alloys, and then again, magnesium in compounds is also quite common and quite important. Finally, the remaining 0.8% is all the other elements from our periodic table, at least the naturally occurring ones there in the Earth's crust. So quite a lot of things to consider, but really, if you can keep silicon and oxygen down as the top 2, then you're in pretty good shape. Now, getting a little more specific than just Earth's crust, let's talk about soil. So soil can be natural or manufactured. So when we mean natural, we're talking about the minerals, clay, broken down rocks, foliage, other organic remains, those various things that just occur naturally in a given area as part of that soil. If we think about manufactured, we're not making soil in a factory. What we mean, at least not generally, right? What we mean there is things that are manufactured products getting mixed in there. So glass is, again, can be naturally occurring. If you get a lightning strike on a beach, you can make some glass fragments that way. They tend to be very beautiful, actually, but they tend not to be terribly common in nature. So if we see glass or cement or asphalt, bricks, cinders, paint, again, those are typically from human activity, things that humans have made. So that's why we would call those examples of manufactured soils. And of course, we can have a mix of natural, so different minerals, clays, all mixed together. We can have a mix of manufactured things, glass and cement and asphalt, or we can have a mix of the natural and the manufactured, which is probably the most common, at least in an area that's been, inhabited by a fair number of people. So a city or even a suburban, or depending where in the rural areas, you might find more or less of that manufactured component in the soil. So there's varying grain sizes, there's different colors, there's a lot of different ways we can classify the soil, but again, it does vary pretty widely over fairly small areas. So that's how come soil can be such an important piece of physical evidence to link suspect to a scene based on the soil evidence that they might have on their person and how it matches or doesn't match the scene soil profile. If we look at the soil in terms of chemical composition, a lot of that will depend on temperature or wind, rainfall, erosion, again, all those different factors that would take place in a given location. So that the particular soil composition, chemical composition of soil in one place could vary drastically over another place, just based on location and based on, if we're talking about seaside location that gets a lot of wave activities and erosion like that, or if we're talking about a forest area where there's a lot of vegetation to hold on to the soil and minimize erosion, if we're talking about a rainforest where you get rainfall frequently, or a desert area where you get very little rainfall, all these different factors can have a dramatic effect on the soil samples and their chemical and physical compositions. Now, looking even deeper at the soil, we can look at some different components. And so we have sand, silt, and clay. And we'll often use the word sand to describe a very specific substance. We'll even do that in the next part of this topic when we talk about glass. But sand is really about a particle size. So sands have particle size of about 0.05 millimeters to about 2 millimeters. And they tend to be the largest of the components of our soil. So next, if we talk about the clays, those are the smallest, with particle size smaller than 0.002 millimeter diameter. And finally, silts are in between. So they would be between that small clay, which we said was less than the 0.002 millimeters. So the silts will be between the 0.002 and roughly the 0.06 millimeters that we would start to separate into the sand, the largest particle size that we start at about 0.06 millimeters up to 2 millimeter diameter. So based on, again, those different components, and you're likely to have all three, honestly, but soils are probably more predominant in one type. So they might be a very sandy soil or a clay-like soil, and that will influence, again, the geology of the area. Sandy soils are going to be better at drainage because they have large particles that allow for the flow of water between them. Clays can have the buildup of water because they are so small, they don't let water permeate as well. So those are some consequences. But of course, in a forensic investigation, we're looking more at, do we have the right soil profile on the suspect compared with the scene. And if we don't have the right mixture of sand, silts, and clays, or at least the major profiles of those particle sizes, then we're likely looking at a soil sample that's not a match for the scene if we compare that particular soil sample from the suspect and come up short on that particle size or grain size comparison. Now, another way we can classify soil is by subcategories based on really the biology and chemistry of that soil. So if we look at peat, for instance, peat is 20% or more decaying organic matter. So there's a lot of formerly living things there. If we think about plants that are decaying or animals that are decaying, they make up a large percentage of that peat. So we tend to find a lot of peat in wet areas like bogs, and so that makes sense because that's where you've got a lot of decomposition occurring. If we think about loam, which is another soil subcategory, that's a mixture of sand, silt, and clay, so those three different particles that we just mentioned. And again, as a result of having a mixture of those three, we tend to see fertility and excellent agriculture from loams. So loamy soil is well suited for growing crops and things like that. Finally, chalk would be very alkaline. It's quite basic if we look at the pH of it, and it tends to be found below the top layer of soil because you tend to see the chalky sort of components concentrate down there. They can be washed down to that level by water, and then they tend to build up there below that top soil, the top layer of soil. So those are three different subcategories, and again, you're likely to encounter all of them, but depending on where you are, you're more likely to encounter loam, for instance, in a farming area than you are probably chalk, or at least at the top layer, you're much more likely to encounter peat or loam than chalk anyway. So keep that in mind as you're thinking about soil and investigating the application of soil to forensic science. Now that we're getting a little more familiar with soil, let's go ahead and talk about the soil horizons, or the different layers where the soil forms. So soil does tend to form in layers, and we just hinted at that with chalk being below the top layer of soil. That gives the idea that there must be other soil layers. So let's go ahead and talk about those. Each one's going to have different characteristics, and there's 6 total layers that exist, but we're going to tend to focus on just the first couple. So the O layer, the humus or organic layer, again, that's where you're going to have a lot of decaying matter. If it's 20% or more, we'd call it peat. If it's less than that, then we would probably call it loam. We're unlikely to find chalk at that very top layer, so those are our most likely choices, but that's, again, where things are growing and happening, and that's why it's rich in water content and a lot of organic matter. Below that is the A layer, or the topsoil, and so that's, again, combined with O. Those are the 2 horizons or layers that tend to be most important in forensic science. Once you get down to E, the alluviated horizon, that's going to be a little less common, of course, unless we're dealing with a burial, right? If someone has dug into the ground any considerable distance, then these other soil horizons could be relevant. But for the most part, we tend to look at A or O soil layers. So if we look now below, we've got B, which we'd consider the subsoil, and then C would be known as the parent material. That's about the last place that roots could go, is down into B and stop at about C there. And finally R, which would be the bedrock. The weathering of that bedrock ultimately is what creates the other layers of soil, but we're unlikely to get down quite that far in terms of forensic science. So that's just more for the completeness sake that we talk about all those different soil horizons. But again, it's really O, the humus or organic layer, and A, the topsoil layer, that we tend to interface with in forensic analysis. Okay, so again, to give a little more detail here, so we talked about the soil horizon as being particularly relevant, and again, that's known as the humus or the organic horizon, and it's made up of a lot of decaying material. That's why it has so much organic content and a fair deal of water content as well as a result. The other layer that we tend to encounter a lot in forensics is the A, or the topsoil horizon. It tends to be very dark colored, and it tends to contain the minerals. Roots will proliferate in that particular layer if we're talking about a place where plants are growing well. And again, it has a lot of water content, so you have to be careful because it might look darker than it really is. When we go to compare soil, we'll look at them dry just so that we have the ability to compare apples and apples, right? If it's wet, it can look a lot darker than that same soil would look if it were dry. So we'll dry the soil before making comparisons. So E, that alluviated horizon, tends to be very light in color. It's mostly made up of sand and silt. And leaching occurs in this layer, and that can carry away valuable nutrients, and so you have to be careful about that because the roots often do go into the E horizon as well, and so we don't want all of those nutrients stripped away if the plants need those to survive. So that may be one reason why synthetic fertilizers might be used in an area if it's difficult to grow the crops needed because those nutrients have been removed by water, leached out by water. As we continue to move our way down, we get to the B, or the subsoil horizon. And again, this tends to hold a lot of clays and minerals stripped from those upper layers, as we mentioned, as they move down through by leaching. This is where the clays, which are the small particle size, they tend to be captured here in this B, or subsoil horizon. Moving on down to the C, or the parent material horizon. Again, this is where we have those rocks that have been broken up a bit. We're going to talk about the hard rock in our last layer, but these are broken rocks. Roots will not typically extend into this layer, right? They tend to stop at the B, or subsoil horizon that we just talked about. So this is a layer that's more for the broken rocks and the inorganic matter, not a whole lot of organic matter down here because the roots don't move into this layer. Finally, the very last layer, R, or bedrock horizon, is rock hard, it's solid. Eventually it weathers and makes more of that B horizon, but again, it's characterized by solid rock, and so therefore it's another region you wouldn't find plant growth, root growth into. Since rocks made up important parts of our last two horizons there, let's talk a little bit about rocks. So rocks are made up of various minerals, crystals that vary in chemical makeup, color, clarity, shape, density, and refractive index. We've already mentioned the idea of using a polarized light microscope to look for what's known as birefringence that can result from the different refractive indices of different minerals occurring together. So that's something that's going to be important here as we consider forensic analysis of soil samples. We can compare grain size with the mineral material makeup of the rock, and geologists can help determine where a soil sample originated from based on that profile of minerals and the different types of refractive indices from those different minerals. So the rocks can give rise to a great deal of information, as well as the soil that has been generated by that rocky matter and the various minerals that make up that region. So as much as I'm sure you've enjoyed all of that throwback to elementary school and middle school and talking about the different layers of the earth and then to the soil and the soil horizons and layers, let's get a little more focused on how all of this relates to forensics. So the overwhelming reason we care about soil so much in forensics is that soil can be transferred, and it can be transferred via things like shoes, clothing, vehicles, particularly tires on the vehicles, hair, nostrils, fingernails. all these different ways to transfer the soil and carry the soil are important in forensic science. The samples from the crime scene can be compared to samples from the victim and the suspect, and from their homes and places that they visited, places they've claimed they visited. We'll talk about alibi locations, right? If they say they went someplace, why don't they have soil evidence from that place? So that's another important thing where now we're looking for things that aren't there as potential breaks in a case. So soil is very useful in forensics because of this idea that it can be transferred and that we should be able to find soil to back up any claims made by the suspect, victim. They should all be able to be linked to the scene according to Locard's principle. So the use of soil evidence to solve a crime was formalized back in 1904 in Germany. This is the first example where it was really the application of soil evidence that was the big break in the case. So the case of Ava Dish. Ava Dish was a woman who had been killed, and what they found was a handkerchief at the scene which had coal, snuff, and the mineral hornblende. And so they looked into their suspect pool, and they happened to find one suspect who was working at a coal burning plant, so that would explain the coal on the handkerchief. And he also worked at a quarry that was rich in hornblende, so that's a reason you would be able to explain that mineral on the handkerchief as well. Snuff was popular then, again, as it had been for a while, so that wasn't such an important piece of physical evidence. A lot of people used snuff, and so it wasn't so relevant as the coal and the hornblende. So looking at the suspect, now at the time, cuffed pants were in style, which was convenient because his pant cuffs had 2 layers of dirt in them. The lower soil layer matched the crime scene, and the top layer of soil in those pant cuffs matched Ava's home, and so that was some pretty damning evidence to link him not only to the crime scene but also to the victim's home, and that was really the evidence that led to his arrest and conviction for that particular crime. So it's not always that clear-cut how soil relates to a crime, but this was a nice example of the first real case that soil was particularly important in solving the crime. Again, it tends to be just a part of the various physical evidence pieces that come together in most crimes, but in this case it was really the major component there. Okay, so looking at how we analyze soil samples to try to make them as useful as they were back in the case of Ava Dish, all the samples should be dry samples. I mentioned that earlier, that even a little bit of water can make the soil sample look a lot darker than it is, and color is going to be a pretty important piece. We see here on the slide one of those color charts, and again, there's hundreds of different colors that the soil can fall into, so it's important that it be a dry sample so that we're assured that the color that we see is really the color that we get. It's not falsely dark because of some soil or some water content of the soil, rather. There's also grain size, so a grain sieve there can be used, a soil sieve can be used to separate the different grain sizes from the soil sample and compare that for the suspect soil compared with the scene soil, and see if the grain size distribution seems to match there. So there's a couple of ways that we analyze soil samples, and we'll go on to talk about a couple more. Okay, so far we've been dealing with naked eye observations. Now let's consider what we can see under the microscope. So under low power, you can often see the organic material from plants or animals in the soil. If you move up to higher power, then you can distinguish the types of rocks or minerals present. If we are talking about a polarized light microscope, you can look for birefringence to make those identifications and confirm indeed the different minerals that you might have present. We can even go to X-ray diffraction, we'll talk about in a moment, or chemical testing if you really need to know for sure what particular chemical makeup is of that soil sample. Now, so far we've been talking about analyses that an expert would make. A density gradient column is a tube with liquids of different densities like we see here. This is one that you could make at home if you were so inclined, if you get really excited about this sort of thing. And those are all non-toxic, although they are going to cause some trouble if you rinse them down your drain, especially the lamp oil and the rubbing alcohol. I'm not sure we want to say they're entirely non-toxic, but they're not too hazardous compared with the liquids that are officially used, which tend to be bromoform and bromobenzene, which are decidedly more toxic. So what you can do with a tube, and the reason bromoform and bromobenzene get used is because they're clear and colorless, so you really get to see the soil. But you take your soil samples and place them into different tubes, and if they fall into the same sorts of gradients, then that's an indication that their density matches. Now we can do this sort of work by X-ray diffraction that we'll talk about in a moment, but the nice thing about the density columns, they're very visual. So a jury that may not have any science background to speak of can clearly see that this soil sample from the suspect's shoes, for instance, matches visually the soil sample from the crime scene, and that can be very powerful rather than a discussion of X-ray diffraction and elemental analysis and things that the typical juror might not feel so comfortable with. This sort of visual density gradient tube approach can be very powerful because it's a very visual method. Now looking at some other features that we can analyze soil for, water content. So some soils are just naturally tackier than others. If we think about Arizona or a dry climate like we tend to associate with the state of Arizona versus New York, which has a fair deal of wetlands and much more water content on average for its soil, then clearly that sort of water content analysis could be valuable evidence. Chemical testing, so if we're just looking at pH, we could tell if it's, an alkaline soil or an acidic soil or, maybe a very acidic soil. That can be helpful information. But if we need even more detail, we can look at the mineral content. Finally, X-ray diffraction can provide a very valuable set of data to allow for matching a particular soil sample from a suspect with the scene. So in X-ray diffraction, the sample is crushed and tested. The X-rays are shined on at various angles and looking for the response from the soil sample, from really those minerals in the soil sample, will interact differently, I should say, with the X-rays. If the X-ray diffraction from the two samples gives a roughly identical pattern, then that's a good indication that they're a match. You could also look at the different powdered diffraction patterns in the sample and match those to particular mineral phases to determine their identities. So it seems a little backwards now to talk about soil sample collection, but we often would talk about the collection before the analysis, since the collection has to happen before the analysis logically. But let's go ahead and talk about soil sample collection now so that we get the analysis done correctly. So the movies and TV shows that you might watch with forensic themes often get this wrong, so don't pay attention when they're scraping things off in the field that they shouldn't be, right? Instead, if you find the soil in whole lumps, collect those whole lumps because they'll contain different layers and they can always be separated at the crime lab rather than out in the field. If we're talking about soil sample comparisons, again, you want to collect from within a 100-yard radius of the crime scene because soil does tend to change even over that small a distance. I mentioned earlier, collect from that alibi location. If the person says they visited a different park or a particular place that was important for their backstory, then go ahead, visit that location, collect some soil from that location. Still at the crime scene, the access or escape routes, right? They may have entered and exited different ways, so you want to have soil profiles from both access or escape routes, or really any route of access or escape. The homes of both the victim and the suspect would be another logical place to go out in their yards and get some soil. You want to be very detailed as to where the soil samples were collected, right? We just mentioned that soil samples can vary over just a 100-yard distance, so we want to be as detailed as possible, and you want it written down because it may be a while before anything comes to trial for the case that you may have been working there. If you see soil on a shoe or something like that, a relatively small object, you want to collect that whole object. You don't want to scrape the sample off. Maybe a large tire or something, it might be acceptable, but if you can collect that whole object, collect the whole object. Don't scrape the sample off in the field. Let the crime lab technician scrape it off at the crime lab. Finally, don't forget to collect comparison samples because you want to make sure that you have those for comparison's sake. So don't just collect, say, bloody soil immediately by the body. Collect some comparison samples, again, within that 100-yard radius, but that are not blood stained, for instance. And then, of course, we want to package everything separately in plastic vials here unless there's biological evidence that's being carried by the soil. Then we would want to do paper bags so that the biologicals don't get contaminated with the molds that would be in the environment. And so here we see some good work on both ends, right? So the investigators collected that whole shoe rather than scraping off the soil. They collected the whole shoe as they should have, and we're assuming that they sent it to the crime lab in appropriate packaging. And now we have our crime lab technician wearing gloves, using forceps, doing the best that he or she can do to analyze that soil sample correctly. So that's what we want to see. Good work at the field end and good work at the crime lab end. So on that happy note, we'll transition here from soil analysis to glass analysis. All right, so now let's shift to our discussion of glass. So glass is a substance made primarily of silicon dioxide, which is often from sand, which is small grains of quartz. And we talked about quartz back in the soil part of this unit because we talked about the most common mineral being quartz based on all of the silicon and oxygen that are in the Earth's crust. So taking that abundant sand, sometimes mixing in a little calcium oxide, which is commonly known as lime, boron oxide, and sodium oxide, which is commonly known as soda, and then heating up that mixture or the pure sand itself, you'll have to heat much higher, closer to 3,000, to get it to melt. As the liquid molten glass cools, the glass as we know it is formed, and so that's what we see here on our screen is cool glass. Now, even though we talk about glass like it's one thing, there's various types of glass. So if it's the really pure stuff, where it's just mainly the silicon dioxide, the little grains of sand that are quartz, that would be known as quartz or fused silica glass. That's chemically the most pure, thermally the most resistant, and unfortunately the most expensive because it has to be heated so high. Soda lime or soft glass, also known as float glass or plate glass, is the most common type you'll encounter. It has the sodium oxide and the calcium oxide to let it melt at a lower temperature, and so it's a lot easier and cheaper to process, and that's why it's so common. Borosilicate glass has boron oxides as well as sodium oxide in it, and leaded glass, as you would guess, has lead as well. Tempered glass and laminated glass are processing techniques to make the glass behave in different ways, and we'll talk about those as well. Okay, so looking at that quartz or fused silica, the purest type of glass made from the really pure sand, where it's essentially just silicon dioxide in the glass. There you have to heat that sand over 3,000 Fahrenheit. So it's going to be the strongest and the most thermally stable, the most chemically resistant glass, but it's also going to be expensive because of those high operating temperatures. One of the benefits is this type of glass, the hot pieces won't crack even when placed right into cold water. Again, they tend to be reserved for high-end applications like fiber optics or halogen lamps or situations where really nothing but the pure quartz fused silica type glass will do. Even little bits of impurities that we'll talk about in the other glasses are just not able to be tolerated. So the applications that call for this type of glass tend to be your higher end applications. So now let's talk about a much more common type, which is the soda lime or soft glass. Again, it's also known as float or plate glass. This is made from sand. All of the glass that we'll talk about for our course is mostly silicon dioxide. So it's all going to start with sand, but in this case we're adding a little bit of soda, sodium oxide, Na2O, and lime, calcium oxide. So that's going to allow it to be much cheaper to make because it's going to have a lower melting point when you've added those two substances. It's not going to be as thermally stable, so if you took a hot piece of the soda lime glass and placed it immediately into cold water, it will shatter, so you don't want to do that. But for things like windows, bottles, jars, it tends to be fine. Again, windows in the Northeast at least, you'll get cold nights and warm days sometimes, but it's not a rapid heating or cooling that would cause shattering, so that's fine for those applications. Because it's so commonly used, it's also recyclable. You can take the pieces and melt them down again and make new products out of that soft glass. So again, one that we're most likely to encounter in forensic science due to its widespread popularity is soda glass, or soda lime, soft, float, or plate glass. All those names for the same thing. So another type of glass is borosilicate glass, and this is sort of a good intermediate between the soda lime that we just talked about and the fused silica or quartz glass that we talked about first. And this is made from sand. Like I said, they all start with sand, silicon dioxide, and now just like soda lime glass, we're going to add soda, sodium oxide, but instead of the lime, we're going to add boron oxide, and so that allows for greater thermal stability. So here you're going to have much less likelihood of cracking if you place the hot object right into cold water. Again, if you allow it a little time to cool before placing it into the cold water, then you're not likely to see any cracking, and that's why it's a good application for things like cooking or laboratory glassware. So if you know Pyrex or Kymax, then those, at least historically, were borosilicate glass. There's a little video there, if it'll work for you, that talks about the United States moving away from borosilicate glass for home Pyrex glassware, and Europe sticking with the borosilicate, and some of those differences. In terms of laboratory glassware, Pyrex is still borosilicate, but for home glassware, oftentimes it's the soft glass instead, and obviously that's for cost purposes to keep those costs down. Leaded glass is another type of glass. It's chemically made from sand, as all of our glasses that we'll talk about start with, but this time lead oxide is added, and that's going to give it a greater density, both physical density and an optical density, so it's going to separate light and have just a very pleasant appeal, and for that reason it's typically used in art glass and fine crystal to get that nice interplay with light, because the light waves bend, giving the glass a nice sparkle. So that's what the lead oxide does. Again, it shouldn't be released too much, but you should probably be careful not to use too terribly acidic drinks there if you're going to drink out of leaded glass crystal, because there is the chance that you'll be releasing lead ion into the substance. So beautiful to look at, but maybe not as practical to use as the other types of glass we talked about. Okay, so now that we've talked about the different chemistries, the different types of compounds used to make the different types of glasses, let's talk about some processing techniques. And again, these are mainly going to be done to the soft glass, the one that we tend to see the most of. So flat glass or annealed glass, which is typically used for windows. This is the soda lime glass, so it's made from that soft glass or soda lime glass. And so the way that it's made is it's heated and then cooled very, very slowly so that you remove any stresses. Now, that doesn't make it so that it'll never break, but it does make it a little stronger. And there's commercials sometimes where people stand on windows and to show how strong their product is, and that's flat glass, soft glass, that's been through this annealing process. The annealed glass will still break. Ultimately, there is a point where it can't withstand the stress and it does break. And because of the annealing process, it tends to make really sharp shards when it does break. So that can be dangerous. It can lead to cuts and things like that. So from a forensic standpoint, it could lead to some blood evidence if the suspect has broken through an annealed glass window, and they haven't done that in a very wise fashion. If they've just done it with their bare hand, then we're going to be looking for a suspect with a cut, and we may have some DNA left at the scene there from the blood. So that's one potential benefit of this breaking in a way that it gives really sharp shards. Now, if we think about the exact opposite of annealed glass, we have tempered glass. So it tends to be more durable than typical soda lime glass. So in this case, we take that soda lime glass and heat it up until it softens. So this part's about the same as the annealed glass, but whereas the annealed glass was very slowly cooled to remove all the stresses, here the glass is rapidly cooled with air jets to create a lot of those stress points, a lot of many random stress points in the glass. So now if something hits the surface with enough force to break it, it's going to disintegrate into a lot of small pieces. So these tiny fragments shouldn't be very sharp. They tend to be quite dull, and so that's a safety feature. So this is used where you might have to break glass. So if you're thinking about your car, the side and rear windows are typically made with tempered glass because heaven forbid you end up in a situation where you drive into a body of water and you need to kick out the windows. Those side and rear windows are going to be able to be broken, not easily. It'll still take some force, but those are the ones that will break in such a way that you shouldn't have really sharp shards. It should be fairly dull pieces if you have to crawl through that broken window to escape your vehicle. And so here we see an image of a rear windshield that's been destroyed, kicked through, or some sort of object has been used to damage it, and you see it's a lot of small and not very sharp pieces that result. So you could theoretically crawl out through that if you had to in order to escape your vehicle. Don't do that with the front windshield. We're going to talk about the front windshield in a moment, but it should work on the side and rear windows of the car. And there's a little video there if you want to take a look at that as well. All right, so now the other glass processing technique that we're going to talk about is laminated glass. And so this is used for the car front windshields. It's also known as safety glass, and in this situation you have 2 layers of soda lime glass, so we're still dealing with that soft glass, right? It's abundant, it's cheap, it's the one that we tend to encounter most of the time in forensics. And in between those 2 layers is a PVB plastic interlayer, and so that's what allows for the broken glass. If one side or the other should fail, usually it's the outside of the car windshield that fails, then the plastic interlayer is going to keep the broken glass in place. It's going to prevent the brake from breaching the inside and blowing into the vehicle and distracting the driver. Obviously the driver is going to be distracted by this big break in the front windshield, but at least they won't be subject to debris and other things blowing into the vehicle through a fully broken windshield. So this is why we would not try to kick out the front windshield if you needed to escape your vehicle. The side or rear windows are the ones to break because this is very strong. That plastic interlayer helps to keep it all intact and again to prevent the failure of the front windshield from causing the driver to be cut or go off the road because of the complete failure of the front windshield. Instead, you've got the 2 layers with that plastic interlayer as a safety feature to keep it all at least intact, even though it will be still quite difficult to drive that way, but at least to get over to the side of the road until help can arrive. All right, now, so if we look at the analysis of glass, we might be looking at a type of evidence that's individual characteristic. If it has those asymmetric breaks or striations that match like a puzzle piece. So in that situation, we can say not only is this the same type of glass, but we can say this piece of glass came from this other larger pattern. So that makes it individualized, like DNA or fingerprint evidence, and so it's quite valuable. That's why we want to treat the glass well, so that we don't have additional breaks, and we'll talk about that in the collection of packaging of glass. Glass may also just be class characteristic. Again, that at least can tell you the type of glass. As we've already mentioned, soft glass is quite common, so it's not going to be probably terribly useful if that's all you can say, but it's more than nothing, and it's certainly worth collecting and considering as physical evidence. You may even get down to the composition or the manufacturer, which does narrow the field down even for some glass that's as common as the soft glass that we've talked about so far. So if our goal is to meet the individual characteristic evidence, then we're going to really try to piece everything together. So we've got to collect all the glass. We want to keep it intact. It's already broken somewhat. We don't want it to break any more under our watch. So we'll collect it all, and we'll make sure that we do our best to wrap it and place it in a sturdy container so that it doesn't break anymore. Now, if class characteristic evidence is all we're able to go after, then we've got to have a way of determining what type of glass we have. So density is an important physical property for analysis of glass. Just like we talked about with the density of soil, we can use those density tubes like we talked about in that part. And that's another reason why we have these two topics together, because they really do have similar analyses and similar ways to compare. So density is the mass divided by the volume, and we have our video link there to show you how you might be able to find the mass of the glass, place the glass in a cylinder, graduated cylinder, to read the volume by displacement, and then subtract out that amount of water that you had in the grad cylinder to find the volume due just to the glass, divide the mass of the glass by the volume of just the glass, and you get the density, and you can compare that density to other samples. And again, depending on whether it's fused silica glass or leaded glass or soft glass, it's going to have a different density. Another physical property that we can consider is refractive index. So how much does it bend light as the light goes through that material? So light waves bend when they penetrate glass or water or a lot of different media. So the refraction changes due to the different densities of the two media. And again, it could be a situation where we might have leaded glass. We talked about that giving that nice shine. Well, it's because it has a fairly high refractive index. So if we need to determine that refractive index, the way we'd go about that is to place that glass sample in a liquid with a known refractive index. If the glass fragment's still visible, something called the Beck line, the ability to see the surface of the glass and the separation of the glass from the liquid, then it must not have the same refractive index as that liquid. And we go on and we try another. If the glass fragment is not visible, the Beck line's not present, it essentially disappears into the liquid, then it has the same refractive index as that liquid, and that's why, being optically matched, it seems to disappear, and then we would know that our glass sample has the refractive index of whatever liquid caused that effect. So that's how we would determine the refractive index for our glass sample. Now, in addition to the information that the glass might give us about the type of glass, and if we happen to be lucky enough to find puzzle piece-like glass that we can get individual characteristics, we can also often use glass to give us more information about how it might be broken if we're dealing with broken glass. So we see here some bullet holes through glass, and so when glass is broken, we get a couple types of fractures. First, the radial fractures, which are cracks that radiate outward. They occur first, and on the opposite side from where the glass was hit. They'll stop when they hit an existing fracture, so you can tell the order of shots, which shot was fired first, for instance, from our picture. This is a little complicated. We'll have a easier to interpret drawing coming up. And then finally, when the bullet hits, less of those concentric circles will form, so that gives us more information about the order and side that the bullet may have entered and exited. So the concentric fractures, again, these are cracks that encircle that impact, and we can see those on our picture as well. So they occur secondly and on the same side where the glass was hit. If rocks hit instead of a bullet, then you'll get more concentric circles to form. So let's go ahead and take a look at some more of this information in a slightly less complicated picture. All right, so here we have fewer bullet holes, so that makes things a little easier. So in this slide, we're going to look at the difference that the direction of impact has. So the entrance side, the side that the object enters from, let's consider a bullet, is going to be smaller and more regular in terms of the hole that you get compared with the exit side, which is going to have a larger, more irregular hole. So if we look on the left, we have the entrance hole. This is again double pane glass, right? So we have it entering one pane and then exiting the other. So it's a smaller entrance hole, and then on the right we see the other side is the exit hole, and it's larger and more jagged. So that's how we can tell if the bullet was fired from outside into the home or from inside the home outside, based on the appearance of that entrance side, which gives the smaller, more regular hole, compared with the exit side, which gives a larger, more irregular hole. Now, in addition to the direction of impact, we can also find the order of impact, and this we can tell by the radial fractures. So if we look here, the radial fractures from a second impact would end at the radial fractures of the first. So if we look at our drawing, on the left we have the first shot, and we know it's the first shot fired because we see that those radial fractures on the right hand side of the image continue. They go further. Compared with those second radial fractures, they all stop when they hit the existing first radial fractures. So that's how we can tell the order of the impact. In this case, the left shot was fired first, and that's why it has longer radial fractures that extend to the right side. The second shot, its radial fractures that extend to the left all terminate on existing radial fractures from the first shot fired. Now, in addition to knowing the entrance side versus the exit side and which shot was fired first and second, we may also be able to get some information about the location from which the shot was fired. So, for instance, if we have a perfectly round hole, the shooter is perpendicular to the glass. If it's more of an oval shaped hole, then the shooter shot at an angle. They weren't directly in front and perpendicular. If the glass shards are more on the left side, then the shooter shot from the right side. Likewise, if the glass shards are found more on the right side, then the shooter shot from the left side. Finally, another lucky break we might get in forensics is the result of backscatter. So if the shooter's close to the glass, then the shards will shatter back toward impact side and onto the shooter. So hopefully they're small enough shards that the shooter doesn't realize that he or she has them on their shoes and clothing, and can later have those found by law enforcement and submitted as physical evidence to indicate that this person was the likely shooter in a particular incident. And if you want some more information, look at our video here. It'll talk about some bulletproof glass, which is unfortunately not a type that we've talked about. It's a polycarbonate material, so it's carbon based, and we've focused only on the silicon-based glass. So there is a whole other type of glass, the bulletproof glass, that we haven't even touched upon, but you could certainly start your search for more information with that link. And to follow up on what we just said, here we see a shot from the left on the left-hand side. And so we notice it's more of an oval because it was shot from the left instead of straight on, which would give a more circular appearance. And notice that hole sort of goes from the lower left to the top right, and we'd expect to find the glass shards on the right-hand side in this case. If we look on the other side, now we have a shot from the right. So notice that the hole is again oval shaped because it wasn't directly in front, it was from the right, and the oval sort of goes from the lower right to the top left. So it's leaning in the exact opposite direction as our shot from the left, and that's what we'd expect since it's from the opposite direction. And we'd expect to find our glass fragments over on the left in this case. Okay, just like we said on the previous slide, the fragments would be on the opposite side from which the shot occurred. So the entrance holes here were fired at different angles. So what's the difference? Well, we just talked about the difference, how the oval leans is going to indicate whether the shot occurred from the right or from the left. So we focused a lot on breaking the glass with either rocks or with bullets mostly, but glass can also fail because of heat fractures. So during a fire, glass can break as a result of that heat fracturing. So how do we know that we had a bullet as opposed to a rock as opposed to just a heat fracture? So here the heat fracture produces breakage patterns that are very different from those caused by impact. You'll get the wavy fracture lines to develop. You'll also see that the glass will feel smooth to the touch. There'll be notable differences there, and that's how you can tell the difference between the heat fractures and the other impact breaks that we talked about earlier. All right, now for our final consideration of glass, let's talk about the collection of glass evidence. So because the glass can break even further, we want to take a photograph with and without scale bars, so a native and annotated photograph for every glass sample that we're going to collect. Photograph first, then you'll try to collect all the fragments, right? If we're going to piece them together, we need to have all of those pieces. We want to check for blood or fiber evidence, so the glass could be a carrier for either of those. So check and see if any of the fibers got caught or if the suspect cut him or herself and left behind some blood evidence for us. We want to package those into solid containers so that they don't break down any further by being packaged inappropriately and subject to stresses that cause further breakage. So hopefully a solid container will prevent that. We also want to collect the suspect's shoes or clothing that can then be examined for the presence of glass fragments, right? We talked about the idea of the backscatter there if the suspect is believed to have broken the glass by perhaps shooting through it, then we'll look for those fragments on his or her person. If we find any, again, individually wrap those in paper so they don't break any further and submit to the crime lab for analysis. So there we have it, our unit on soil and glass analysis. Hopefully you saw that soil and glass had some similarities, and that's why they were logical to put together here, and hopefully you're eager to move on to the next unit. I will see you there.